All right, so let's start with some questions. If you have any questions.
I think it's a bit late for me to ask about this, but I kind of have a bit of an issue with the multiplets.
Yeah, sure, no worries. I'll ask away.
Yeah, that thing, the diagram that you showed a few classes ago.
Yeah.
Could you explain that a little bit, like in a broad sense?
Sure. Let me just first bring up the lecture notes, because I don't want to. Okay, I think I can try to actually guess. It might actually be better. Let's take an example. Okay, let's take an example of a, say, I don't know, like a spin half particle, two spin half particles. Okay. So if I look at, so this is particle A, and this is particle B. Now, if I look at the Hilbert space in a dimension of HA is going to be 2, right? And the dimension of HB will be 2. So that means that the dimension of HAB, which is a tensor product, so the Hilbert space of HAB is made out of tensor products of HA and HB and all their linear combinations, right? So what would be the dimension of this?
4.
Yeah. Is it because 2 plus 2 or 2 times 2?
2 times 2.
Right. Okay. Now, if I call this, say, J1 and call this J2, if I look at how the multiplets would combine, what would be J? This is the highest value of the total angular momentum operator. So the total angular momentum operator is J, and that'll be J1 plus J2, right?
Mm-hmm.
Do you agree here? Yeah.
Yeah.
So we want to find out the eigenvalue of the total J. The highest eigenvalue is going to be what? J1 plus J2, right? So that's going to be what? 1. So what will be the dimension of this multiplet?
4.
What is 2J plus 1?
Oh, right. No. Yeah.
What is it?
It's going to be 3.
Yes. And then there'll be another multiplet where, it'll be J1 plus J2 minus 1, which in this case is what?
2. It's 0.
Yeah. So what will be the dimension of that multiplet?
It's going to be 1.
Right. So these two will add up to what? 4.
4.
Okay. Now so there'll be 2 multiplets. First, we make the multiplet where, the total angular momentum, it's J squared. Let's call it J. Yeah. That'll be, so that'll be J, 1 times 1 plus 1, right? Because we know that the angular momentum of J squared is going to be J times J plus 1, right? Mm-hmm. And there's H bar squared, which I'm just, yeah. So this is going to be, this is 2, but of course that means that its eigenvalue, which is, say, J, I know that I've defined J to be just this thing, so let's call this J prime, okay? So J prime is the total angular momentum quantum number. Then this is equals to 1, right? So first, we want to find out what the multiplet for this thing is, right? So we start with the highest weight representation, which is going to be the total angular momentum, the highest weight state here, which will be 1, 1, right?
Yeah.
You agree?
Yeah.
Yeah. And then we're going to apply the J minus operator, which of course is equal to J1 minus plus J2 minus. And this, of course, is going to be, the first particle, its spin is spin half. And, it'll be a linear combination of, not linear combination. This will be this state, right? This is A, right? I mean, does this formula make sense?
Yeah, well, I'm not too familiar with this, so I can't really say much.
What do you mean you're not? I mean, we did a whole lecture, 2 lectures on this, right?
Yeah, I still need to get used to this term.
Yeah. So okay, what I'm trying to say here is this following. This is a crucial thing. You need to understand this, otherwise. So yeah, this. Let me. So so this equation implies this equation, right?
Mm-hmm.
So, that means that also, this equation implies Jz is equal to J1z plus J2z, right?
Yeah.
Then this particle, so this is the total, and this is the angular, this is the total angular momentum number, and this is the
So
z
this is just the
component.
tensor product of the two states, like two half of
Yeah,
states.
exactly. And this one will have to be the addition of this half plus this half, right?
Yeah,
Otherwise,
now I got it. Yeah.
this formula, right?
Yeah.
Because if we apply this formula to both left-hand side and right-hand side, you have to get that, you must be able to get Jz, you must get this, right? H bar 1, 1.
Mm-hmm.
And the only way you're going to get this from here is if, this is how you're going to get, right? There's no other way you can get this, right? If you put a minus sign here or a minus sign here or 1 minus sign, 1 plus sign, it's not going to work. Okay?
Mm-hmm.
Right.
Yeah,
So
got it.
now basically you have, the highest weight state, and then you apply to it your J minus operator, and on the left-hand side, you're going to get 1, 0 state. And on the right-hand side, this thing is going to act on, so this term will first act on this thing, and this term will act on this thing, right? So the first term, like this, will become some C1, which you can figure out. And then this will be half, comma, minus half, tensored. So this is A, half plus half. And there'll be another term, so this is B. Another term where this will be half, half. And the second factor will be half minus half, right? So that we see that we have Jz, Jz is minus half, Jz1 is 1 and minus half here, or A, and Jzb is plus half. So these two will add up to 0. Same, Jz A is half here, JZB is minus half here, right? So again, this will also add up to 0, and this is exactly what we get here, right?
Yeah.
Okay. And then you can apply the J minus operator again, and you're going to get 1 minus 1. And here, what will you get? You can guess, you will just get this thing. Okay?
So we keep
Right?
on using the J minus operator on that
Yeah,
state.
and then if you apply J minus again, you're not going to get anything. And this is the multiplet with the three-dimensional multiplet we talked about here, right?
Yeah.
So let's draw a figure. And in the figure, we said that, okay, this is going to be the highest weight state. Okay. And as we apply, the J minus operator, it's going, so this is, okay, this axis is going to be the JZ value. Okay. And if I apply the JZ operator, I'm going to get another state. But its value will be, JZ value will be 0, right? And that is this state. And here we have this state, okay? So, you see that you might ask, why didn't I draw it here, right? Well, yeah, I mean, logically, as long as it's somewhere on this line, it still has the same value JZ, right? So, just indulge me. So if I apply the J minus operator, I go from here to here. If I apply the J minus operator again, I go from here to here, right? And this is the 1, 1 state. This is the 1 minus 1 state. And this is the other state that I, over here. Let's call it, yeah, it's 1, 0. Now the time comes to work out what this other, multiplet is. And there's only one, there's only going to be one state there. And what is the total angular momentum? It's 0, right?
Yeah.
So the total angular momentum will be 0. So it can only have, its Z component can only have one value, which is 0. Now, how can we have Z component, which is 0? Of course, we must have, it must be a linear combination of this thing. So here, let's get C1, let's C2, okay? So this linear combination is taken by this state. So what we do is that we say, okay, let's just take this, what we have here. It's a good thing. We don't want to waste it. And then we just write, what we do is that we just change the sign here. If we change the sign, then it becomes a different linear combination. It becomes a linearly independent state, right?
Mhm.
With the same normalization. And
Yeah.
so this is going to be this. So this has 0, right? So then we are saying, okay, so this state is in a different Hilbert space, but it has the same JZ value. Okay. So if instead, we had, different values of J1 and J2, then of course what we would have is that, this guy would be longer, and this would not be one-dimensional, and we would have something like, blah blah. I'm not going to be like rigorous here. I'm just going to make stuff up. It'll be like something like da 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 da, and there could be something like da 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 da, and this is like one Hilbert space, one multiplet. Okay, sorry, it's not reading my mind. When apps don't read your mind, that's really annoying, right? Read my mind app. Here, see, now it's reading my mind. Okay, even then, it's not perfect. Yeah. Anyway, and then this could be another one, and this is another one, right? Does that clarify things, Josh?
Yeah, that clarifies a lot, actually. Thank you, sir. Yeah.
Okay. Yeah. Okay, so this is just a pictorial way of representing the different multiplets. Okay, any more questions?